Here I'll teach you about the SR latch. So as we know that we have four types of latches: the SR latch, JK latch, D latch, and T latch. So I'll teach you only one latches, so which will actually help you to generate or understood the other latches. Let us go through latches, okay? And the SR latch is made up of the NAND gate. So SR means set and reset, okay? So SR latch S stands for set and R stands for reset. So if you take a NAND gate here, okay, the NAND gate 1, another NAND gate here, the gate 2. So the output of NAND gate 1 is like Qn, and here it is Qn complement. Okay, so we'll have one input that is S, another input here that is R. So here one input, another input of gate 1 is connected to output of gate 2, and another one input of gate 2 is connected to output of gate 1. Okay, this is the basic circuit of SR latch. Here we'll study about the truth table. Okay, we'll design the truth table. And one more important thing, to design the truth table, you should not change the input simultaneously. That means you take a note, change one input at a time. Okay, so you should change one input at a time. And you can see, as we are connected, we have used the NAND gate, we should have the NAND gate truth table. So this is A, B, this is Y. So you can see 0, 0, 1, 0, 1, 1, 1, 1, 1, 0 is 1, and 1, 1 is 0. Okay, so NAND gate. The truth table of NAND gate is. So from this truth table I can see, irrespective of the input, if you have at least 1 0, then your output will go to high. Okay, if you have any 1 0, don't bother about other 0, then the output will go high. Okay, so to design the truth table, we take you have to take input S and R. Here we take Qn and Qn complement. Okay, so these are the four input and output, so you can get the state here. Fine. Okay, first I'll define 0 and 0 in S and R. So S becomes 0, R becomes 0. The behavior of NAND gate is, if any one input is 0, the output will go to high. From this truth table you understood this thing. So the output of inverter 1, the output of NAND gate 1 becomes 1. Right? So once the output becomes 1, similarly for the NAND gate 2, one input is 0. So irrespective of the another input, the output also go to 1. Right? So the for input S and R to 0, 0 will get Qn1 and Qn complement 1. So is it possible? No, because when I take A is equal to 1, A complement should be 0, right? That means if you take Qn is 1, Qn complement should be 0. But this is not possible. That is why this state is called invalid state. Okay, this is invalid, not possible. Then after, with the note, I know that change one input at a time. So what I do, I make R to 1. Okay, when I make R to 1 and I see what happened when I make R to 1, so this 1 and previously it was 1, both the input of NAND gates are 1 and 1. So if both the inputs are 1, output will go to 0. So here I'll get the output as 0. Okay, once I get the output 0, that 0 is applied to the input of 1. So previously it was 0, now it was also 0. So 0, 0 is 1. I'll get 1 once again. So I can write here, when I make 0, 1, I'll get 1, 0. That means Qn is my normal output, Qn complement is my complemented output, so I should bother only about the Qn, and we can say Qn becomes 1. We can write Qn or output bit is set. So we can say set, right? Okay. Now I know that I have to change one input at a time. So if I make 0, if I make S to 1, R to 0, here 0 changes to 1 and 1 changes to 0 is not possible because both the inputs are changing. I have to change only one input. So let's make this S to 1. Okay, when I make S to 1, the inputs are 1 and 1, right? So when I make S to 1, see here I get 1, here it is previously 0. So any one input is 0. So output go to 1, fine. And here it is 1. Supply to input of get 2. Here it is 1 previously. So 1 and 1 gives 0. It becomes 0. And see 1 and 0. Before applying 1 to S, the inputs are 0, 1 and the outputs are 1, 0. Now if I change only S to 1, becomes the input becomes 1, 1 and output remains same, that 1, 0. So we can write this is the previous state. Okay, previous state. Fine, because output never changes if I change S to 1. Then after S is 1 already, I make R to 0. So if I make R to 0, I'll get 1 and 0. Once I make R to 0, so previously it was 1. So input to the inverter 2 is 0 and 1. Any one input is 0 means output is go to 1. And this one is again fed to inverter 1. Here it is previously 1. So 1, 1 go to 0. So the output becomes 0 and 1. 0 and 1. Here my normal output is Qn. As my Qn becomes 0, you can see it is reset. Okay. This is reset. Okay, fine. So from this table, if I want to clearly draw or clearly write the truth table, S, R, Q and state or Qn, the state, we can write like this: 0, 0 is invalid, 0, 1 is 1, that means set, 1, 0 is 0, that is reset, and 1, 1 is the same state. We can write Qn or we can write the previous state. Okay, we just copied with some modification. So this table belongs to the SR latch, which is made up of NAND gate. Okay, I told you if you design the truth table of NOR gate, you just change the position of Qn and Qn complement. So if you change this position, this comes to here, this goes to here, this comes to here, and this goes to here. We'll just interchange the outputs. We'll get 0, 0 as Qn previous state, 0, 1 as 0 reset, 1, 0 as 1 set, and 1, 1 as invalid. Okay, this is the SR latch using NOR gate. Fine. So if you remember any one table, or if you understand to how to derive this table, you can understood everything. Okay, and you can see in one of the state we will have invalid condition. Okay, that is why this is the demerit of the SR latch. So to overcome this invalid condition, we will go for JK latch. Okay, And you will remember one thing. So SR latch is the best latch or best flip-flop to eliminate the switch debouncing. That is a very important concept. Okay. So from next lecture we'll study about the flip-flops.